Hi, good evening to one and all. Once again, I welcome you all to the thermodynamic course. So, in the previous lecture, we discussed about the basics of thermodynamics and terminology. In today's lecture, we are going to discuss about basic laws of thermodynamics and the thermodynamic equilibrium also. Right. So, in the basic law of thermodynamics, as per the syllabus, actually, we are having the first unit is nothing but the first law of thermodynamics and its limitations. So, the basic law of thermodynamics is nothing but actually we are going to discuss about the zeroth law of thermodynamics and after that the first law of thermodynamics. Right? Yes. See, first we'll enter into with respect to the zeroth law of thermodynamics. So the zeroth law of thermodynamics is nothing but basics for thermodynamic equilibrium. So, in order to discuss about the thermodynamic equilibrium, we supposed to know this zeroth law of thermodynamics. See, what is that the zeroth law of thermodynamics we are having? The statement is nothing but very simple. See, when a body A is in thermal equilibrium with a body B and also separately with a body C, right? Then the body B and C will be in thermal equilibrium with each other. So, this is what your simple statement for zeroth law of thermodynamics. See here, the body A actually we are having the body A separately thermodynamic equilibrium with body B and body C. Got it? See, this is nothing but we are having the thick line. So, here actually we are having the connection between the system A as well as the system B. Over here also, we are having the connection between system A and C. Got it? But B and C, we are not having any connection between these two systems. But even though all these three systems will attain the thermodynamic equilibrium. That is what your zeroth law of thermodynamics. Is that right? See, listen here. The A is nothing but actually we are having separately thermodynamic equilibrium with system B. And A also, it is having separately thermodynamic system with respect to C. But B and C also will attain the same thermal equilibrium. That is what this zeroth law of thermodynamics states. Right? So, with respect to this thermal equilibrium, we have explained. Is that right? So, for example, we can able to consider with respect to the temperature. For example, we can able to consider the A system is nothing but 25 degrees Celsius. Right? And the B system actually we are having around 15 degrees Celsius. And the C system actually we are having the 35 degrees Celsius. Got it? For example, you just remove this system C. Only this A and B are interconnected. What will happen actually? We'll reach the thermal equilibrium state, right? With respect to the temperature 17.5 degrees Celsius. When the system A and the system B reaches 17.5 degrees Celsius, then the system A and B attains the equilibrium condition. Got it? Similarly, with respect to A and C, right? We are having A is nothing but 25 degrees Celsius and C is nothing but 35 degrees Celsius. So, the average is nothing but actually we are having around 30 degrees Celsius we are having. So, until it reaches A and C system separately with respect to 30 degrees Celsius, it attains a thermodynamic equilibrium. Got it? So, with respect to separate cases, we are having the separate values. Here I said it is nothing but 17.5 degrees Celsius, right? Sorry, 25 plus 15. So, we are having around 20 degrees Celsius we are having over here. And over here, for example, we'll consider, right? So, for over here 25 to 35, we are having the average is nothing but 30 degrees Celsius we are having. Right? So, this is actually separately with respect to AB and AC. But we know that this A system is nothing but connected with B separately and connected with C separately. So that the thermodynamic equilibrium is nothing but we won't get 20 degrees Celsius or we won't get 30 degrees Celsius. We'll get the some other degree Celsius. Right? That is in between actually 15 degrees Celsius to 35 degrees Celsius we are having. That is what this law of thermodynamics states. So, this is what a simple zeroth law of thermodynamics and the application point of view is nothing but we can able to use with respect to the equilibrium conditions, right? So, here actually we have considered only the thermal equilibrium and we can able to consider with respect to mechanical equilibrium also. So, with respect to the pressure or with respect to forces, we can able to say, right? So, this is the basic law of thermodynamics we supposed to know before entering into the equilibrium conditions. Right. See, after that actually, once you discuss about the zeroth law of thermodynamics, what is happening actually? We are having with respect to the thermodynamic equilibrium, right? So far I said, in order to attain the equilibrium conditions, actually, we supposed to use the zeroth law, right? So whenever we are having the equilibrium conditions, then it is easy to solve the problem, right? We can able to simplify the equations and we can able to get the solutions also. For that only we are using this thermodynamic equilibrium or equilibrium conditions, right? Yes. See, the thermodynamic equilibrium, first of all, actually, we are having with respect to the various three categories we are having. See, first one is nothing but actually we are having as mechanical equilibrium, right? And the next one is nothing but chemical equilibrium we are having, and the last one is nothing but thermal equilibrium. So while discussing with respect to the zeroth law of thermodynamics, we discussed with the thermal equilibrium, right? So, but the major three types actually we are having with respect to mechanical equilibrium, right? And after that we are having chemical equilibrium and then thermal equilibrium. See, mechanical equilibrium is nothing but actually it comes under the parameters as forces or pressure, we can say, right? Or load acting. And the chemical equilibrium is nothing but the reactions and the products, right? And the thermal equilibrium is nothing but actually we call it as major thermodynamic properties, or we can say simply energy parameters also. So these are the various three categories we are having. So before that, before entering into this various types of equilibrium, right? What is meant by first of all equilibrium, right? When the system we can able to say it attains the equilibrium conditions. Got it? See, for that actually we are having the definition over here. A system is said to exist in a state of thermodynamic equilibrium. See, in that thermodynamic equilibrium, it might be with respect to mechanical case, or it might be with respect to thermal case or chemical cases also, right? We can able to say, right, the system exists in a state of thermodynamic equilibrium when actually when there is no changes in any macroscopic property is registered, right? So in the earlier example actually we discussed with respect to the temperature, is that right? In similar way, see, what is that macroscopic property we are having? Already in the previous lecture we discussed about macroscopic and microscopic viewpoints, right? So the macroscopic property, for example, I can able to take with respect to the thermodynamic properties, like we are having the temperature, right, with respect to state 1, T1 and P1, right, pressure with respect to point 1 and volume with respect to the 1 state, right? So these are all comes under macroscopic property. See, there is no changes in the macroscopic property. Got it? If there is no changes in the macroscopic property, then we can able to say the system reaches the thermodynamic equilibrium. Got it? Right? So with respect to that, actually we are having the various categories. Say for example, with respect to that system A, see here, with respect to system A and system B, we are having this system A and system B is interconnected. So it can able to transfer, for example, for a while we'll consider the energy transfer takes place between the system A and between the system B, right? The macroscopic property, I can able to consider the temperature over here. So the temperature is nothing but 25 degrees Celsius for the system A. And what about the temperature for the B system? We'll consider as 15 degrees Celsius, right? So when the system A reaches 20 degrees Celsius, obviously the system B also gains the temperature, right? Energy, it gains energy. So the temperature get increases, it reaches to 20 degrees Celsius. Got it? So now actually the 20 degrees Celsius here A system and here also 20 degrees Celsius. Now there is no changes with respect to the macroscopic property. That is all the temperature, right? Then we can able to say the both the system A and system B reaches the thermodynamic equilibrium. Got it? So this is a simple example we can able to go with respect to the thermal equilibrium, right? Yes, in that also already we discussed various cases we are having. First one we'll discuss about the mechanical equilibrium, right? So what is that mechanical equilibrium we are having? See, when the system we can able to say it exists in the mechanical equilibrium, the thermodynamic equilibrium, this is a general one, right? So in that actually we are having three categories. One is nothing but we are having the mechanical equilibrium. See, listen here. In the absence of any unbalanced force, right? In the absence of any unbalanced force within the system itself, right? or we can able to say between the system and surrounding, between the system and surroundings. Got it? So any unbalanced in the sense, so both the forces with respect to the system and surrounding or between the two systems got balanced, right? So that is what actually we can able to say it exists in the form of mechanical equilibrium. Got it? So always with respect to the forces, right? If the forces acting on the system are balanced, it might be with respect to reaction forces or whatever you have applied the forces, right? So we can able to say with respect to that it is a balanced one. Then I can able to say the system attains a mechanical equilibrium. That is what they have mentioned as absence of any unbalanced forces, which means the forces are getting balanced. Getting balanced, then I can able to say that system is nothing but we call it as mechanical equilibrium. Got it? Right? And next one is nothing but we are having the chemical equilibrium. Right? So the chemical equilibrium in the term, so from the term itself actually we come to know there is no chemical reaction. So in a system, right, we can say a system is said to exist in a state of chemical equilibrium when no changes in the chemical reaction, right? There is no changes in the chemical reaction, or we can say transfer of matter from one part of the system to the other part, right? One part of the system to the another part, right? Then we can able to say this system reaches the chemical equilibrium. Got it? So whenever there is no chemical reaction, then we can able to say it reaches the chemical equilibrium. So the reactant A plus B, we are getting equal to product C, right? So until this A plus B get reacted, and after that there is no chemical reaction takes place, it produces the new product C, right? Then we can able to say now the system attains the chemical equilibrium. But in our syllabus actually we are having only with respect to the physical equilibrium. Physical equilibrium in the sense mainly we need to focus on mechanical equilibrium as well as thermal equilibrium. So as per your syllabus actually we are having mainly with respect to mechanical as well as thermal equilibrium as the thermodynamic equilibrium. Got it? So for the chemical engineering purpose actually we require this chemical equilibrium also, right? So the next one is nothing but thermal equilibrium, right? So the thermal equilibrium is nothing but there is no spontaneous changes. There is no spontaneous change in any property of the system. Got it? Any property of the system is nothing but there is no spontaneous. See, listen here. We know that from high to low always it moves. That is what the spontaneous process. Got it? See, now the system A reaches 20 degrees Celsius and the system B reaches the 20 degrees Celsius. Now actually the system A and system B, it both are having same temperature. So there is no spontaneous over there. Then I can able to say the system reaches the thermal equilibrium. Got it? So this is what actually the thermodynamic equilibrium we are having with respect to the thermodynamic systems. Between the systems or between the system and surrounding also we can able to say. That is what we have included here. Between system and surroundings or between the systems also it is applicable, right? So this is what the various categories actually we are having the thermodynamic equilibrium. So for this actually we require that zeroth law of thermodynamics, right? So this is actually we have discussed only with respect to the two systems. So if I'm having multiple systems also, we supposed to use that zeroth law of thermodynamics. Got it? So right, we'll move to the next law of thermodynamics. So as we know the zeroth law of thermodynamics, that is the basic law for the equilibrium conditions, right? And next actually we'll move to the next law of thermodynamics, that is nothing but first law of thermodynamics, right? So this is a very basic law actually we are having. As per your syllabus actually we are having the first law of thermodynamics as the first unit, right? So that is what we have discussed the basics of thermodynamics so far, and basics of terminology also we have discussed before entering into this first law of thermodynamics, right? So in simple statement actually we are having the first law of thermodynamics is nothing but the conservation of energy we are having, right? So the conservation of energy in the sense everyone knows that law of conservation of energy, is that right? So that is stated with respect to the scientist Gibbs in 1873 he stated. What is the statement actually given? That is what energy can't be created or destroyed, only transferred by any process, right? So we know that the energy conservation principle. So energy neither be created nor be destroyed. Only we can able to transform from one form of energy to another form of energy. So that is what the transferred by any process, right? Like the heat addition process with respect to the constant volume or constant pressure or constant temperature process, whatever it may be. So with respect to any process, in the sense, in that process I'm having two state. One is nothing but initial state, and after that I'm having final state. That's it, right? So this is what actually we are having the first law of thermodynamics. But the first law of thermodynamics with respect to the thermodynamic system, got it? With respect to the thermodynamic system, we need to apply, right? See, with respect to that closed system, it is very easy to understand the first law of thermodynamics. The closed system is nothing but actually we are having a non-flow system, right? So in the closed system, always the masses are conserved, right? So we can able to apply only with respect to this first law of thermodynamics for the closed system. It is very easy to understand the basic parameters. For example, if I set thermodynamic system, see if whenever I'm having the thermodynamic system, obviously we supposed to have, right, with respect to the heat addition process or heat energy transfer. So I'll consider the closed system. Inside that we are having the working substance. The working substance may be in the form of liquid phase or in the form of vapor phase, whatever it may be. So I'll consider this as mass of the system equal to 1 kg. Mass of the system equal to 1 kg, right? So the mass remains constant even after completion of the process, right? See, that is what for the closed system actually we are having the simple energy parameters. One is nothing but we are adding the heat energy. So that is what the thermodynamic system we are having. So how to apply this first law of thermodynamics to here, right? So whenever we are having the energy conservation, so in the thermodynamic system we are supplying the energy. In that way we'll assume that is the simplest way. I am supplying the heat energy to the system. What will happen actually? See, the thing is that if one of the boundary is movable, for example, if the one of the boundary is movable, but even though it is closed one, the mass remains conserved over there. What happened? The heat energy is converted into other form of energy. What's that other form of energy? Initially, I'm having the internal energy of the substance, working substance as U1. So that is what U1 is states actually before starting the process, right? After heat addition process, the system reaches with respect to U2. That is what the final state, right? So this is what actually we are having as available energy in the system, right? So that is what actually we term it as internal energy. Got it? See, if I add the heat energy over there, what will happen actually? The internal energy of the system increases. So the heat energy is transferred to the internal energy, right? If I'm having the movable boundaries with respect to the closed system also, then what happen actually? I can able to get the mechanical work done, right? Or we can say with respect to the displacement work done, right? Because of the flow of the gases, right? Because of the flow of the working substance. So there actually I'm having the flow energy as well as with respect to the mechanical displacement over here. If I have the movable boundary, got it? So these are the basic actually parameter we are having with respect to the closed system. If I consider the open system in the sense, the mass also actually need to transfer from one system to another system or from system to the surrounding, right? So it comes under the flow process. So in the next topic, we'll discuss about the flow system or open system. So for the simple case, actually, I can able to explain with respect to the closed one. See, now actually I have added with respect to the heat energy, right? The heat energy is added, and that is actually converted with respect to, see, listen here, this W is nothing but actually we are having the mechanical work done, or we can say displacement work done. So displacement in the sense to and fro. So I'm having the movable boundary over there. and this del U is nothing but the internal energy change, U2 minus U1. Right? So this is what the conservation of energy. How much energy I have transferred actually? That is with respect to the heat energy here. The heat energy is nothing but actually Q. Q is nothing but actually we are having the heat energy. Right? So that much energy is transferred with respect to the internal energy, with respect to as well as mechanical work done. Right? So only these three parameters actually I am having with respect to the closed system. Now this satisfies the first law of thermodynamics. Right? So in the other way also we can able to mention the Q equal to, we can able to mention with respect to W plus del U. W plus del U. So this is actually with respect to the del U, we are generating the heat energy. That also we can able to consider. But always the desirable one is nothing but we are supplying the heat energy to the system. Right? So that is converted into with respect to W plus del U. Both the conditions satisfies. So majorly we are having only these three energy parameters. Got it? So this is what the law of conservation of energy with respect to the closed system we can able to apply. Right? See here. So the net change in internal energy, the net change in energy is equal to the heat that flows across the boundary. See, boundary is nothing but actually we are having over here. These are the boundaries. Right? So I said one is nothing but the movable boundary. If I arrested all the boundaries, what is happening actually? The mechanical work done is 0. So work done will be 0. So whatever the heat energy you have supplied, that is stored as the internal energy. Got it? Right? See, that heat flows across the boundary minus the work done by the system. Right? So in the slide it is actually they have given. Here also they have considered as the heat is added to the system. If heat is added to the system, then obviously the heat flows across the boundary. Got it? So the condition gets satisfied. So this is what actually the law of conservation of energy. So how much energy you have transferred actually, assume that with respect to a particular value, 100 kilojoule per kilogram. Why? Because the mass is conserved over here. So that is why the energy parameter I am going to consider in terms of kilojoule per kilogram. Right? So 100 kilojoule I have transferred through the heat energy. That energy how we got actually from the calorific value of the fuel I got. Right? So from that actually this 100 kilojoule is converted into the other form of energy. What is it actually? Internal energy as well as mechanical work done if I have the movable boundary. Got it? So that is what the statement says. So this is actually we are applying the first law of thermodynamics to the thermodynamic system. Right? And two, this is nothing but actually we are having only with respect to the closed system. Right? So you can ask me, what about the kinetic energy we are having? What about the potential energy we are having? Right? So those things actually we can able to assume with respect to the open system. Whenever the mass transfer takes place, right? There actually I can able to apply with respect to the other form of energies also. But the major three energy parameter for the closed system is nothing but heat energy, work done and internal energy. Right? See, this is what actually see here, where Q is heat and W is work done. Some heat flowing into a system is converted to work and therefore does not augment the internal energy. Right? So if it is converted into work done actually, so it won't augment the internal energy. The internal energy remains remain same. But the macroscopic property of the working substance also will changes. The pressure get increases during heat addition process. The temperature get increases. So the momentum of the particle keep on increases. The momentum of the particle or working substance keep on increases. Then the internal energy also get changes. Right? So that is what the statement. So this is a simple first law of thermodynamics I can able to apply with respect to the closed system. Only these three energy parameters I can able to consider. Got it? See, in detail, if you want to say with respect to the what is that various terms actually we have discussed: heat, internal energy, and work done. I said mechanical work done. I said, right? So this is what actually consideration actually with respect to the solving the problem. So with respect to heat addition, if I add the heat energy to the system, so in which way I supposed to consider, whether it is in the positive way or in the negative way. So the sign conversion also I supposed to consider, right? See, listen here. The origin of thermodynamics deals with always the heat, right? The heat is nothing but the form of it is a form of energy we are having, right? It depends upon with respect to the change in the temperature of the systems. Got it? So the thermodynamics is nothing but thermo consider heat and really any energy as though it were an indivisible fluid, right? and it allows flowing from higher to lower energies always. That is what actually we are having with respect to the spontaneous one, right? So this is what actually we have given as the heat energy. So always the heat energy is nothing but actually flows from higher to lower energies, right? So with respect to the sign convention, see, energy flows from the surrounding to the system, right? So the sign convention is nothing but or positive when the energy flows from surrounding to the system. So the system is nothing but actually I supposed to consider for the analysis purpose. Inside that actually I am having the working substance. This is the system. It is surrounded by the surroundings, right? This is surrounded by surroundings, and we are having this system is nothing but A. In between actually the surrounding and system actually I am having boundaries. Got it? So if the heat transfer takes place from surrounding to the system, then I supposed to consider in terms of positive, right? And if it is in the vice versa manner, reverse manner, then I supposed to consider in the negative manner. So when the energy flows from system to the surrounding, so which means it loses some energy. The energy transfer, heat transfer from system to the surrounding is nothing but actually we are having with respect to the negative sign. So this is all we supposed to consider universal one, right? For the calculation purpose, it is required, right? So this is about actually heat energy we are having, or form of heat actually we are having. And another one is nothing but actually we are having as internal energy, right? So whatever the energy you have supplied to the system, heat energy supplied to the system, that is stored with respect to the internal energy. That is what we discussed, right? So with respect to state U1, that is what the initial state, and another one is U2, final state. So U2 minus U1 is nothing but we are having in terms of del U. So there also, if I got the del U as positive or negative, right? So it depends upon the whether the internal energy increases, then I'll get del U equal to positive. That is what the desirable one, right? If the internal energy decreases in the final state, what is happening actually U2 minus U1 will be negative, which means we are transferring energy from the system to the surrounding again. Got it? So it becomes as a negative. So we discussed in the heat energy. So this is what actually we are having internal energy, right? See here, the heat energy here as heat added is nothing but always positive, right? Heat added is nothing but actually always we are required with respect to the positive manner. Got it? So in the next slide we'll discuss about the other energy parameter, that is what work actually we are having, right? See, the work is nothing but we are having in terms of, see, in the flow system we'll consider the flow energy or flow work also we are having, right? So with respect to the flow of the working substance, so it can able to transfer the energy. That is what the flow energy we are having. It comes under flow work done. But for the closed system, actually, we are not having any flow over there, right? So we can able to consider only with respect to the displacement work done or mechanical work done. See, work is nothing but another kind of energy we are having. See, if it is with respect to, if I can able to measure this mechanical work done with respect to the Newton per meter, what is happening actually, that is also comes under form of energy, right? So how much force it is required to displace the particular movable boundary to the distance, right? So that is what F into S is nothing but actually we call it as work done. So what is that actually we are having the standard SI unit Newton per meter. Newton per meter is nothing but always joule, right? So it is also another form of energy we are having. Got it? See, it is different from the heat, that always knows, right? So in order to sense the mechanical work done, actually we require the movable boundaries, right? So if the movable boundaries, if I am considering, so how much pressure is acting on the movable boundary? So it is nothing but the pressure is nothing but actually we can able to get from the momentum of the working substance, right? That pressure I can able to convert that in terms of force parameter also. So this much load is acting on the movable boundary. Got it? And how much it get displaced with respect to that, I can able to sense the energy, right? So this is what actually we call it as the mechanical work done. And we can able to say with respect to the mechanical work done, which is positive actually, if I am extracting work done from the system, right? So that is what your ultimate aim for the heat engine, right? For the engines actually, we are supplying the heat energy and that is converted into form of mechanical work done. So that is what actually we call it as a desirable one. So whenever we are getting the energy work output from the system, that is nothing but always positive, right? If I am supplying the work input to the system, that is nothing but always nothing but we call it as negative, right? Like compressors we are having, pumps we are having. So for that actually we supposed to supply the work input to the system. Got it? So these are all actually we are having the various forms of energy parameter with respect to the closed system. See, not to discuss the first law of thermodynamics, these are all primary energy parameter we need to know, we supposed to know. See, listen here, this is what actually we call it as the mechanical work done, right? So I said with respect to how much distance it's moved, right? So the distance and as well as with respect to, see, I can't able to take only with respect to the force parameter, that the pressure is responsible. Why? Because these are all comes under a basic thermodynamic property. So basic thermodynamic macroscopic properties are nothing but we are having a PV diagram and we are having a TS diagram. So the basic one is nothing but actually I'm having pressure, temperature and volume and entropy and enthalpy, that we will discuss later, right? So these are the macroscopic properties we are having. So how much force is acting, actually I can able to convert that in terms of pressure parameter. So if the pressure parameter takes place, actually I supposed to calculate with respect to the displacement volume, right? So how much the volume get displaced. So which means in the 3D I supposed to sense. Got it? So this is what actually we are having with respect to the work with respect to the first law of thermodynamics. So how to sense that, right? So with respect to the macroscopic property, actually I'm having only the pressure we are having. Got it? Only with respect to the pressure. See, pressure unit is nothing but I'm having Newton per meter square, standard SI unit, and this is nothing but volume change is nothing but meter cubic I'm having. So this also will provides Newton meter, right? So that is also nothing but the force into displacement. But according to the thermodynamic system, we require the macroscopic property, thermodynamic property, that is nothing but the pressure, right? So I need to sense the pressure and temperature and volume of the particular thermodynamic system with respect to initial and final state, like P1, V1 and T1. Similarly, P2, V2 and T2. So with that I can able to explain this work on the first law, right? So this is about actually the basic law of thermodynamics. So far we have discussed, and this basic law of thermodynamics is applicable actually with respect to the thermodynamic equilibrium. And once you're done with the first law of thermodynamics, for simple understanding purpose, I can able to consider with respect to the closed system. So with that closed system, I can able to easily sense what are the basic thermodynamic energy parameters actually we are having. That is what actually we have discussed so far. So this is about today's lecture. So thank you everyone. So in next lecture actually we'll discuss about the various quasi-static process. Thank you.